we just looked at some examples of so we looked at a regression tree, a very simple regression tree, and we looked at an example of a classification tree. And next we're going to talk about how one would grow such a tree. So growing a tree in a good way, preferably get a tree which has good performance. So before I get into this, let me just briefly mention I only described examples in the case where the features of x here were real valued. So each coordinate was real valued, but this algorithm can be extended in a very it's still efficient and extended in a very natural way to the case when the features are, say, integer valued, or even more generally if they're not even ordered, but they're, say, just categorical, just some from some finite set. So how do you construct one of these things? Well, it turns out that there's not a way to get the optimal tree. So there's some optimal tree of the types that I described above for minimizing the training error, but what we can do is use what is called a greedy algorithm. This is what people usually do, because finding the global optimum is well, at least nobody's come up with an efficient way to do it. So what's the greedy algorithm? So a greedy algorithm in general is one where at each step you choose the optimal decision, and at the end you get something which may not be globally optimal, but it might be reasonable. So I'm going to talk about this in the case of regression. So let's call this RD, just some abstract, make a little more space there. So this is just some abstract cube here, some multi-high dimensional cube, and maybe this is the first coordinate, xi1, I'll denote xi1, maybe this is xi2, and maybe this is xi3. And there's more dimensions, but unfortunately I can't draw them. So we've got this high dimensional space here, and what our greedy algorithm is going to do is it's going to find, so at the first step, so we have to construct this binary tree, right? So at the first step, it's going to choose the coordinate and the split that minimizes the error. So let me make that a little more precise. So we've got, so let's define the following quantity. So we've got a sum. So we've got, remember we had in the case of regression, we had this error function. So we have, so let me write it this way. So we've got y, we've got the min over all y's, y minus yi, summing squared. This is our loss, and where I'm going to make this sum over i's such that xi is greater than s for some number s. Oh, I should say xi, let's make it xij is greater than s, because our x's, right, our x's are these points. Xi is some point xi1, xi2, up to xid. So we're going to sum over those i's for which xij, the jth coordinate, is greater than s. And we also have this part. So this is going to be the greater than part. Xij greater or equal to s. Y minus yi squared. So this minimum, remember, this is the the same thing here. We wanted to get the y, but the quantity is the same thing we were minimizing over this region. So here we're choosing the value y, which minimizes this error over the region. So if, for example, if we had so if j was 1 and s was whatever this quantity is here, then we would split along here and we would get this region where it's less or equal to, this one should be less or equal to. So we'd have the region where it's less or equal to all this stuff over here, and we would choose the y to minimize our error in this part for this one, and then for this one we would choose the y to minimize our error on this other part. And so we will choose for the first split, choose j and s. Let me make some room here. To minimize this quantity. Right? So any given j and s, for any given j and s, this quantity is well defined. And we can find, so we can do this efficiently because, well, there's only finitely many, j only goes from 1 to d, and for each j there's only, well, there's of course infinitely many possible real numbers s that we could split this dimension along, but since we only have finitely many data points, right, we only have, there's only finitely many points in our data set, it turns out that we only need to consider finitely many splits s. So that's the first step, the first split. We choose this s and j, and maybe say it's this one. Say we get this one. Now, so that determines our first node. Now let's say we're going to look at this one. So now we have this region over here. Say maybe it's this region on this side. And let's call that region R. So for the next split, or say, so for splitting region R, we're going to do just the same thing, essentially the same thing. So we'll choose j and s to minimize the min over all y's, and now we're only going to sum over i's such that both xij is greater than s and xi is in R. Because we're only considering now the subset of points that are in this region. So we're restricting our attention to this region. So we started out with all the data, we split it, and now this one's just looking at R. When we split that, maybe we split it here. Something like this. Right, so this was our first split, was like along this plane here. Now maybe this is our second split, so here, this would be like, that was our original S, and then this was like, the next S, maybe you call it SR or something like that, to split R. And then continuing, so now that gives us our split for this node, and we can continue, maybe we need to do this one. So for this one, we would again get a new region. Maybe we call this one, I don't know, R prime or something. This region above, so it's to the right of S and it's above SR. And we just continue doing this same procedure here. So this, we recurse on this step. So we split, so we would split R prime and we would take this to be R prime. So this gives us a way to construct this tree. We just keep doing it. And as I've described, this procedure would just keep going on infinitely. So how do we stop? When do we stop? Well, we could stop. So one way to stop is we could stop when, there's only one point x in R. So if we get to some R that has only one point, we don't split. Or another thing, which probably is a little better strategy, is to only consider splits. So here we were considering arbitrary splits S, but we could consider, so option A would be only consider splits resulting in regions with greater or equal to some parameter, some number of, say, I don't know, 5 points per region. So we could do this. And so you would modify these splitting steps so that you would make sure that whenever you split, you always end up with at least 5 points in each region. Or, replace this by any number m, some minimum number. So this would be some parameter that you would choose. So typically what people do is follow this type of greedy procedure to grow a regression tree. And then, well, typically what then people do is they use what's called a pruning strategy to reduce to prune the tree back, because for statistical reasons, which we'll talk about later, it turns out that gives you better performance. But what we're going to do instead is take the random forests approach, and we will talk about a different way to handle the problem that you end up with by growing a full tree, even if you use this parameter to limit things. So we'll use the randomization techniques of bootstrap aggregation and random subspaces to get better performance. So this is how you grow a regression tree.